Perform AC/DC analysis on this multi-stage amplifier given beta equals 200, early voltage VA equals 100 volts, IC1, or the collector current through the first transistor T1 here, equals 1 milliamp, and IC2 equals 0.8 milliamps, which is also going here. So at this point, I expect you to know the basics of how to perform AC/DC analysis of single transistor amplifiers for both common collector, common emitter, and so on and so forth. But if you don't know how to do that, I have my analog playlist in the description below, so you can check that out to learn the fundamentals. So anyways, let's get started. Under DC analysis, we first need to find RE1 and RE2, since in this problem, we are actually not given what these resistor values are. So let's start with RE1, where E means emitter, since this is the base, collector, and emitter, as you know. So for RE1, we need to do DC analysis, of course, in which caps are open. Therefore, we don't need to look anything to the left of this capacitor, nor to the right of this capacitor for transistor T1. Redrawing the circuit, we have our 12 volt source from the top, feeding into resistor RB1, or R biased one, which is also connected to RB2. Followed by the BJT, and we don't need to know what's on the top yet. However, we do need to add RE1. Don't worry about the capacitor since it's also open. We must find the Thevenin equivalent to actually perform a KVL loop. So V Thevenin is the voltage division across RB2, since that's the potential being amplified through the resistor. So 1 mega ohm over 1 mega ohm plus 1 mega ohm, since they both have identical values, RB1 and RB2. So that will just be 1/2 times the original voltage value of 12 volts. And intuitively, this is 1/2 times 12, which will give you VTH of 6 volts. For RTH, take them in parallel like usual, which should give you 500 kilo ohms. Since we are taking two equivalent values in parallel, you divide by 2. And now we can redraw the circuit with the new values. So 6 volts goes into the Thevenin equivalent resistance of 500K. Into the transistor. And then we have RE1, which we are going to find now. We should also keep in mind the 0.7 voltage drop that will occur across the base emitter barrier. Since we're given that IC1 equals 1 milliamp, I'll write that here, we can confidently assume that IE1 is roughly equivalent to IC1, which also equals 1 milliamp. And since beta is a fairly large value, they have an insignificant difference among each other, so we now know the currents going through both these nodes. Of course, we need to find IB before we can perform KVL, since we need only one variable in this equation, RE1. And given our small signal parameter formulas, we understand that IB1 equals IC over beta, which equals 1E negative 3 amps over 200, which gives you 5 microamps. We can now make our equation. So 6 volts, starting from the left here, equals R Thevenin, which is 500 E 3 ohms, times the current going through IB, which was 5 microamps, or 5E negative 6 amps, plus the 0.7 volt barrier, plus, again, we have to now consider RE1, which is the only variable in this equation, times the current flowing through it, IE1, which is approximately IC1, which is approximately 1e negative 3 amps. Moving the non-variable terms to the left, we can subtract the 6 volts by 0.7 volts plus this product, which would end up yielding RE1 times 1e negative 3 amps equals 2.8 volts. Dividing that by the current, you get your RE1 value of 2.8 kilo ohms. We now must repeat this process for RE2. Moving on to RE2, we must do the exact same thing as before, in which we perform DC analysis where capacitors are open. But this time, everything to the left of this capacitor doesn't matter, and everything to the right of this capacitor doesn't matter. So now we're only focusing on T2. Drawing the equivalent circuit, we again have 12 volts going into RB3 of 100 kilo ohms, connected to RB4 of, again, 100 kilo ohms, feeding into T2. We don't need to know what's up here yet. And we have RE2, which we're trying to find. The Thevenin voltage. And if you use a little bit of your intuition, you can immediately realize that the Thevenin voltage should be the same as before, since we're just taking the voltage division of RB4 over the sum of RB4 and RB3 times 12 volts again. So it should equal 6 volts, but for the sake of clarity, I'm just going to write that down real quick. This equals 1/2 times 12 volts, and again, V Thevenin is 6 volts. R Thevenin, however, will be different. We'll call R Thevenin 2. You can also call this V Thevenin 2, but that doesn't really change anything since they're the same. R Thevenin 2 equals 100k in parallel with 100k. Divide those by 2, you get 50k since they're the same value. And we can now redraw this with our new 6 volts attached to R Thevenin 2 of 50k. Going into T2, attached to RE2. Remember the 0.7 volt jump, and we can do KVL2. But right before we do that, let's quickly write down that IC2 is equal to 0.8 milliamps. And just as before, IE2 is roughly equivalent to IC2, which is 0.8 milliamps. And IB needs to be evaluated. We'll call IB2, where IB2 equals IC2 over beta, which equals 0.8 e negative 3 amps over 200. And moving that down here, IB2 equals 4 microamps. Let's now make the equation. Starting from 6 volts on the left, we can set that equal to the resistance R Thevenin 2 of 50k times its current, which we just found to be 4 microamps, plus 0.7 volts. And going down here, we have RE2 times IE2, but we're trying to find RE2, so we'll keep that as the variable, times 0.8 e negative 3 amps. Rearranging, we can move the variable to the left side. And after a little bit of simplification, we get our new voltage value of 5.1 volts. Dividing that by the current, we have our RE2 value equal to 6.4 kilo ohms. Let's move on to the small signal parameters now. In regard to small signal parameters, things are going to have to be a little more cumbersome than before, because now we have to consider 2 transistors, so we're going to have to effectively duplicate our process. So I'll put T1 on the left and T2 on the right. Splitting that in the middle, we can now evaluate for R pi, RO, and transconductance GM. So R pi 1 for T1 equals thermal voltage VT over IB1, since we are considering IB1 going from here. This will equal 26 millivolts over our evaluated 5E negative 6 amps or 5 microamps. This will give you 5.2 k ohms. For RO1, we can find it by taking early voltage VA over IC1, where we're given VA equals 100 volts, and we know that IC1 equals 1 milliamp or 1E negative 3 amps. Doing this gives you 100 kilo ohms. Lastly, transconductance GM1 equals IC1 over VT, which equals 1E negative 3 amps over 26 millivolts. GM1 equals 38.46 millisiemens, or times 10 to negative 3 Siemens. Repeating this process for T2, we have R pi 2 equals VT over IB2, which is different than before. It's 26 millivolts over 4 microamps this time, which equals 6.5 kilo ohms. RO2 equals VA over IC2, which equals 100 volts over 0.8 milliamps, which equals 125 kilo ohms. And lastly, GM2 equals IC2 over VT, which equals 0.8 E negative 3 amps over 26 millivolts, which equals 30.77 millisiemens. We now have all that we need to perform AC analysis for this circuit. Now let's perform AC analysis. We know that caps are now shorted. So that means we now have to include the voltage source, R sig, RL, and so on and so forth. But we must keep in mind what type of amplifiers these are when drawing the equivalent circuit. So for the first one, T1, let me draw that here. We can see that there is a resistor on the collector, so it can't be common collector. And the emitter does have a resistor. However, under AC conditions, this cap shorts, so it becomes a common emitter amplifier without degeneration. Looking at this stage, we have T2, which we can immediately see there's no resistor in the collector up here. So we can confidently assume that this is a common collector. So now let's draw the equivalent model. And while you're doing this, make sure to make a lot of space since there are a lot of parameters for this. So we have, of course, V sig directly connected to R sig, which is connected in series to R Thevenin 1, where we found it to be 500K. In parallel to that, as usual, we have R pi 1, which we found to be 5.2K, and all of these are grounded. Now we have our dependent current source, GM Vpi. You can call it GM Vpi1 or GM1 Vpi1, where this is the voltage Vpi. And connected in parallel to this, we have our resistor RO1, followed by RC1. And that completes the first stage of this amplifier, T1. Fortunately, all of this is grounded, so it's nothing too complicated yet. However, what we need to do now is connect this top potential, which is still the collector up here. If you can see, this is the collector, in which this capacitor shorts and immediately touches the base of this transistor. So we can now move on to our Thevenin 2. Which we found to be 50K. And the top of that potential is connected to our pi 2, which itself is the potential V pi. And we know our pi 2 equals 6.5K ohms. And the dependent current source, GM2 V pi 2, which is then connected to our final resistor by the collector, RO2, which is 125 kilo ohms. And keep in mind that the top is grounded since 12 volts is a non-oscillating potential. However, we do have to connect the bottom here for the emitter. And since this is the pi equivalent model, it looks a little weird, but we now have to connect RE2, which is down here, which shares the same bottom potential as our Thevenin, or just ground. And we know RE2 equals 6.4K. And don't forget our load, since we shorted the capacitor up here, which equals 50 ohms. And the voltage out is across RL. So I believe this is the correct formation of this entire AC equivalent model. It's pretty big, but it's fairly informative of how the circuit operates. I'm now going to make some room so that we can find R-in, R-out, and AVs of each stage. So for the common emitter amplifier, for T1, we know that R-in 1 equals our Thevenin 1 in parallel with our pi 1, or 500K in parallel with 50K, which ends up equaling 5.15 kilo ohms. Our out one is also pretty straightforward. It's just RO1 in parallel with RC1, which is 100K in parallel with 4K. And that equals 3.85 kilo ohms. For AV1, we know that since common emitters create an inverted amplification, we should expect a negative number, which is fairly big, hopefully. And this formula is negative GM R out 1, which equals negative 38.46 E negative 3 Siemen times R out 1 of 3.85 E3 ohms, and this equals negative 148 volts per volt. So it is a number that we expected. Now for the second stage, we have Rn2 for our common collector, and this equals our Thevenin 2 in parallel with our pi 2 plus our E2 in parallel with our L, times 1 plus beta. Filling in these variables, we get 50K in parallel with 6.5K plus 6.4 kilo ohms in parallel with 50 ohms times 201. Since beta is 200, you just add 1 to that. And this product gives you 12.39 kilo ohms. So R-out2 equals RE2 in parallel with R-pi2 plus R-out1 in parallel with R-thevenin2 all over beta plus 1. Rather than our previous common collector video where we used R-signal instead of R-out, we have to understand that since there's an amplifier prior to this common collector amplifier, the common emitter, we must account for the output resistance of the entire circuit and treat that as R-sig rather than R-sig being immediately connected to the base of BJT T2. So I'll just note that here, this used to be R-sig if it were for a single transistor amplifier. It should make a little more sense when we make our second multi-stage equivalent model, but for now, let's fill in these numbers. So R-out2 equals 6.4 kilo ohms in parallel with 6.5 kilo ohms plus 3.85K in parallel with 50K over 201. And this gives you an R-out2 equal to 49.7 ohms. This is looking good since we know that for common collector amplifiers, the input resistance is high and the output resistance is low to form a voltage buffer. Lastly, it's automatically known that common collector amplifiers have an amplification of 1 volt per volt. That's it. Now let's move on to our final equivalent model. So for this model, all we are considering are the input and output resistances, as well as the amplifications of each stage. This is very good for calculating the entire amplification of the circuit rather than just AV1 or AV2. And unfortunately, you can't just multiply AV1 times AV2 because that's not accounting for any resistances. So let's start with V-sig again. This is, as we know, connected to R-sig of 1 kilo ohm. And this is connected to R-in of 5.15K. We can just ground this. And now we're looking at the amplification of the voltage drop potential, which is Vin1. And now it is a dependent voltage source. So we're going to have to use the plus minus. We can ground that, and we will call this AV1 Vin1. We know that that is equal to negative 148 volts per volt since it's just the amplification of the first stage. And connected to that, we have our out1 equal to 3.85 kilo ohms, which is directly connected to our in of stage 2. I'll write that down here. Our in2, which we know is 12.39K. Of course, we have our second dependent voltage source of the potential drop of V in 2, which is AV2 V in 2. We can again ground that. And this is connected to R out 2, which we found to be 49.7 ohms. Lastly, we have to consider our load, which simply equals 50 ohms. And of course, the potential across this is V out. We know that AV2VN2 is 1 volt per volt, or the amplification of stage 2. And this is everything we need to calculate the final amplification of the circuit. For a little bit of clarity, we can call this T1 and call this T2. Keeping all this in mind, we know that AV, or the AV final, you can call it, of the total circuit equals V out over V sig, which is equal to the following: R in 1 over R in 1 plus R sig. Since this is the potential being amplified, we are doing the voltage division effectively of these two resistors. This will be multiplied by AV1, which will be multiplied by, now looking at the output of R in 2 over R in 2 plus R out 1, since this is now the potential that's being amplified on the second stage. And you multiply this by AV2, which you finally are looking at the output of T2, which is the voltage division across RL, since that's where V out is, over RL plus R out 2. All we need to do is plug in the numbers and we'll have our answer. Thus, AV equals 5.15 kilo ohms for R1 over 5.15 kilo ohms plus 1 kilo ohm times negative 148 volts per volt times R in 2, which is 12.39 kilo ohms, over 12.39 kilo ohms plus 3.85 kilo ohms for R out 1 times 1 volt per volt times RL, which is 50 ohms, over 50 ohms plus 49.7 ohms, which was R out 2. Putting this in the calculator, you get your final answer of negative 47.4 volts per volt. If you've made a lot of different assumptions than I have for, let's say, thermal voltage, you might get a slightly different answer of plus minus 0.2 volts per volt, but as long as you're in this general area, you're good. So I hope this walkthrough made sense for you. If you have any questions, please leave in the comments below, and good luck.